debugging kind of thanks. Thank you, Renata, for squeezing me in. So my talk will be on the phonon broadening methods from lattice dynamics calculations and neutron scattering measurements. I know probably my previous work with JJ on the thermal conductivity is more proper in this workshop, but I believe there are some what I'm presenting here has some aspects that's related to this workshop. Firstly, it's a phonon broadening, which is related to the lattice dynamic, like thermal properties of the minerals. And even though I'm talking about metals, but a very simple metal. Also, it's a joint effort of theory and experiments. So we thought of the goal to better understand the physics behind basically from a joint effort. The last but not least is this work is funded by DANCE project, which is actually software development, software infrastructure development, which is a multi-university effort to trying to contribute to the community. Basically, DANCE is distribute data analysis for the neutron scattering experiment. And the experiment we are doing are carried out in the spallation neutron source in Oak Ridge. A very brief introduction is that lattice and harmonic effect. In the experimental side, we observe like finite thermal conductivity, but another direct effect is when you do the measurement on the phonons, you actually see the phonon light shapes broaden and shift due to the lattice harmonicity. Even though the theory behind this has been developed in the 1960s by Meredith and Cowley, it hasn't been really implemented very well until recently, like what we have implemented for the lifetime, or the inverse of which is the broadening. And we use, in this talk, I will use aluminum as a typical example for the DFT calculation because it's a free electron system that works very well with the DFT. And also the neutron inelastic scatter measurements. I guess that's one of the motivations, like the major motivation we wanted to look at aluminum is that our experiment shows large broadening in the phonon density state at elevated temperatures. So we wanted to look at that to see, because it's a metal system, so you expect the electron-phonon interaction is important, but how about the phonon-phonon interaction? So this is the computational software and hardware we used. And mostly for the energy and forces, we use VASP to calculate. Here's we use LDA exchange correlation functional and potential with the well-converged setup parameters. And with the for the harmonic phonons and their lifetimes, we use our in-house codes. And the calculations are done in supercell technique. So it's 108 atom supercell, and the cap points is 2 by 2 by 2. For the Bernoulli integration, we use the 24 by 24 by 24 for the lifetime calculations. And the computers we used is Foxtrot, which contains 408 cores, which I think will be free to community. Basically, you can, if you want to do virtual scattering simulations, you can apply the account and you can use the cluster. Here's basically the first step you wanted to do for the lifetime calculation is get the force constant correct, and for the phonons, because the phonons are the basis for the perturbation theory, using the Fermi-Golden rule. So that's the first step to get the harmonic force constant. So I have listed some of the typical Of course, there are many more, like Gigi just taught, but what I'm presenting here is basically the force constant projection along the bound direction. So those are the major terms, and you can see the major terms comes from the first. For the harmonic, we have the on-site force constant, but for the third order force constant, due to the symmetry, those terms vanish. And the leading term instead is a first neighbor interaction. And we see the oscillation of those force constant, which actually reveals Friedel oscillation effects. And the rough computing hours we used for the force constant, harmonic force constant, is rather quick because the aluminum system, and we only have one irreducible displacement for the calculation. So that's take roughly 2 CPU hours because of the supercell. And also for the third order, then the irreducible terms become larger, and that takes about 100 CPU hours. But if we take those on the cluster, so just 1 hour is enough. So since the phonons are the basis for the perturbation series, so it's important to get them right. So this is showing basically the phonon dispersion of our calculation compared with the neutron triple axis measurements. So that assures us we are using a good basis set. And the time for this is trivial because it's just a diagonalization. It's not, it does not take very long.
This is static, right?
Right, it's static. Here's the phonon language we got from the calculations, and the solid curves are computations, and the symbols with errors are from the same experiment as basically Stemmons and Nielsen's in 1960s. That's the only available experimental data for, but it's nice because for most of the system, like neutron data, they don't really give you the line width information. They usually give you the phonon frequency because it's harder to get to the kind of sort out the instrument resolution and trying to get the phonon language out. So but basically we see the top panel is the LA mode, and the down two are the next two are the transverse modes. We see the largest, basically mostly inharmonic modes are those near the X point for those longitudinal mode around X point, and the computation for the phonon language roughly for each Q point takes about 72 because but the real calculation actually takes much more than this because we wanted to do convergence tests. So lots of convergence tests, especially for the like energy conservation and momentum conservation is trivial, but for the energy conservation, it's we need to test that carefully because it's their function. Okay, sorry. So this is like I want to show you three-dimensional, but I think it's easier to see it this way because this is a projection into several high symmetry planes. You can actually give great detail about the language distribution over the Brillouin zone, and you can see that the highest, the most harmonic modes are near X point. Okay, how about the thermal effects on the lattice strain? Because we are doing, all the calculations we are doing for high temperatures are based on the equilibrium volume we calculated from the LDA. But we tested this, like we used, also used a 300 Kelvin expanded volume, but you can see the comparison is really, I mean, the effects are really small, so less than 1% for most of the modes. Here's the scattering kinematics. We have two effects for the lifetime. One is the potential, one is from the scattering kinematics. And this clearly shows all sorts of the scattering channels, and those actually you can see from the scattering kinematics is basically the decay channel from LA mode to 2 transverse mode are responsible or clearly associated with those mostly harmonic modes. Here's the distribution at room temperature and their temperature dependence at high temperature. Basically, I only select a couple of modes here, but they often just increase with temperature because more scattering processes are. Here's how about phonoelectron and phono interaction. We got this is from literature. So I try to, my units are MeV, but I already converted to the same units as they're used. But you can see that even at 0 temperature phono, there are certain Q points that are comparable or even larger than the phono-phono interaction. But for most modes, phono-phono interaction still dominates. Okay, finally, so for the phono-density state, we used the damped harmonic oscillator model to represent each phono, and we got the phono-density state. And at several temperatures, comparing with our experiment, which is in dashed lines, computations from the are the solid lines. You can see the basic information we get from out of this slide is that for the aluminum at high temperatures, phono-phono interaction actually dominates, and they are responsible for the phono broadening. And also, I guess you can see it in the summary here. Yes, so the third point, like even though I just repeat the second one. The third one is the scattering phono-phono, third order phono-phono interaction is responsible for the broadening of phonon dust at elevated temperatures, as we observed in the experiment. And this is our major scattering channels I said in the previous slide. And this calculation demonstrates that our ab initio method is capable of predicting a harmonic effect, which can be used to decouple the electron phonon from end the phono-phono interaction from the experiment. We can help that. So the future work will be, we are doing the systematic study on the FCC metals and the BCD metals. And of course, it would be nice to include a harmonic shift so that we get the self-energy of the phonons. Then we have the harmonic correction to all the thermodynamic properties. Thank you.